Just crossing my fingers to make sure the live stream works. It seems to work. This is great. Let's get everything on the screen in the size that people need it to be. Let's go to, oh, it's me, PCC. You know it's me, buddy. All right, great. Let's share a screen. Hey, Zoom. Yeah. Hey, oh, great. Great question about ANOVA in the chat there. Actually, I think I saw that. I actually thought about that last night, so it's great to ask it this morning. Homepage. That's us. There we are. Statistics 2. We're back. Uh, there's me. Hello, me. I don't want to see that. That's not a nice thing to look at while I talk to people. Let's cover that little picture of me up on my screen with something better, a list of y'all. Welcome, welcome, welcome to Jacob Shore, Lauren O, Lauren R, Quincy D, and Ryan N. Maybe it should have been Jacob S. Welcome, 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 welcome. Awesome. Yeah, this is good. Our question in the chat says, oh, before we get to your homework question, which is a good one, let's go gaze upon our schedule. And while we're on the path there, let me just say, you might not believe it, but I did score midterms between last class and this class. And I made sure to update everyone's homework scores and feedback. So double check in the grade book that all the homework that you have submitted has a score. And, check out my little notes I write you about the topics to give you something more to think about. And double check that your midterm score is there. When you look at the midterm and grades, you can see comments on your work. There's like a rubric that has your score for each problem, along with my comments on your work. Sometimes I make a comment, even if you got 5 out of 5 points on a problem, if there's something, if I want to make a comment about how good your work was, or if there's like a small issue that wouldn't cost you a point, but would be, a nice little comment to make. So check out the comments on your midterm. There might be some stuff to think about. And of course, if there were issues with your work, in those comments, there'll be some tips, maybe some examples of how to do things or suggestions about work we can do together to do better as we go forward. So great work on your midterms. Again, one more apology for the very slow feedback. I still have one class's midterms to grade, and then I'll just be normally behind on everything. But again, thank you for your patience. There are some folks who have not completed their midterms yet. Those of you who've made plans with me and have been talking about your progress, mellow, keep at it. Let's keep working toward the dreams of getting everything finished on the schedule we're on. If anyone who has not taken their midterm is hearing my voice, either right now or in the future on the YouTube video, please reach out if you haven't talked to me yet about your plans. I want to support your success and your learning in this class, because I want you to succeed and, more importantly, learn stuff while you're here. Okay, I'm going to look at just double check our schedule to double check today's plan. Let's make it big enough for my eyeballs. Where are we? We are in the world of Tuesday, the 4th day of March. And we're going to talk about the next topic, inference for the slope of a regression line. Good topic. And a pretty cool one, because it takes advantage of some of the work we've already done and develops it further. So that's a good topic. And I think we're right on time. Last class, we did talk about fitting a line by least squares regression, if I remember. And I think we got all the way through the discussion. Good work, Gus. Okay, so that's the plan. We'll talk about that third section of chapter 8. Bonus note, our topic for Thursday, if you're one of those types who likes to do the reading before our class discussions, we have a topic called More Inference for Regression. Not the best title in the history of titles, though it could have been called Margins of Error for Regressions. regression predictions. Kind of a longer title. In any case, it's like the ANOVA calculations section. It lives in a supplement that lives right in D2L. So let me just remind you where those are. Your last reading and your last assignment for the quarter, they live in content. And just like that ANOVA calculations section, they're in text and technology. Down below both editions of our textbook and below ANOVA calculations, you'll find your little friend, More Inference for Linear Regression. Just like the ANOVA calculations PDF, you can open it up right here in D2L. It was written by Emiliano Vega and myself for you and other PCC students to cover a couple of topics that are not in the textbook, but that our Math 244 instructors here at PCC felt were important enough to include in the course. So we did our best to write it for you. As you read through, you'll see the topics are, well, the first one's not bad. Confidence interval for the slope of a regression line. That'll build directly on top of the discussion from today. And then it gets into see that prediction interval for a response value. What the heck does that weird phrase mean? We'll talk about it on Thursday. And then there's also another funky technique called where is it? It's called, oh, maybe that is the whole list of techniques, but we'll figure it all out on Thursday. But remember, if you like to read this stuff and get some ideas about examples before Thursday, read this More Inference for Linear Regression. Cool. Okay, now there's a great question in the chat from Quincy. Catching up on ANOVA homework, can we go over in the first edition textbook 743, that problem? Yes, we totally can. I actually saw this question yesterday as I was scoring homework, and I kind of wrote up an approach to it in the class notes like late last night, so you might not have seen that yet. But as I wrote it up, I thought, ooh, that last couple things I did would be better discussed in person. So this is a great time to just talk through my notes on this exact problem. So I'm going to go straight to our class notes. There we go, class notes. If I refresh our ever-growing table of contents, looky there, Monday, March 3rd. We don't normally make class notes on Mondays, but 7.4 homework question, 43rd problem in chapter 7. It's called Coffee, Depression, and Physical Activity. Hey, I've got 2 of those down. I got to work on that third one, though. All right, let's check out the problem. I love it when I want to go right to something I've already typed in here. I've got the little searchable. Look at that, so classy. Okay, not everyone has worked on their ANOVA homework yet, so let's look at this together. Coffee, depression, and physical activity. Caffeine is the world's most widely used stimulant, whether in coffee or in tea. With approximately 80% consumed in the form of coffee, and the remaining 20% mostly in the form of delicious, delightful tea. Participants in a study investigating the relationship between coffee consumption and exercise were asked to report the number of hours they spent per week on moderate, that is, like brisk walking, and vigorous, like strenuous sports or jogging, exercise. Based on these data, the researchers estimated the total hours of metabolic equivalent tasks, MET, per week, which gives a positive value. The table below gives summary statistics of metabolic equivalent tasks, MET, for women in the study based on the amount of coffee consumed. Well, sorted out by how much coffee they drink. Okay, this comes from the Archives of Internal Medicine. Now, this problem's got it all. Coffee, exercise. Oh, they're not making the direct connection to depression here in this problem, so let's not worry about, I think these data show up in some other problems as well. maybe there we learn more about connections to depression. Okay, I got a question about C, is what I wrote about last night, but let's look at A first. Write hypotheses for evaluating if the average physical activity level varies among the different levels of coffee consumption. That's not too bad. They're talking about variation in average physical activity level. We're in the world of ANOVA, so null hypothesis, no variation in mean MET physical activity level among different levels of coffee consumption. That might not be the best way to phrase that, but is it clear enough for people to feel that works? That would mean it would be the same mean MET for women drinking up to a cup of coffee a week, 2 to 6 cups per week, 1 cup a day, et cetera, et cetera. All 5 groups, all 5 means, all 5 groups means same. Groups MET means are the same. A different way to phrase it. And alternatively, well, we're checking to see if that average physical activity level varies. So I'll just say, yeah, I just type it like that. Mean physical activity level, MET varies. And I'll just say among the groups, among the different. Oh, I'll just type it again because I feel like it. Levels of coffee consumption. Oh, then or all 5, or there's variation among the groups means. No problem. Okay, that's part A. Part B, check the ANOVA conditions describing any assumptions we need to make to proceed with the test. Conditions. Let's take them one at a time. The first condition is we need what condition do we always need met in every single inference technique we use? Sample data that is independent. Great. People are tapping their return on their chats at exactly the same time. Great work. Independent data. I have to look back up at the description of the study. I've only read it once yesterday and once today. It doesn't describe anything about the sampling technique to find the 50,739 women whose data are collected in this study. Though, if it's in the Archives of Internal Medicine, that's a medical journal. I'm going to assume they used randomness in their sampling process. So no individual women's exercise levels or coffee consumption directly impact one another. Like you wouldn't want 2 best friends in the data set who jog together every day and then go grab a coffee when they're done with their jog. That wouldn't make any sense. Likewise, there's an example in Statistics 1 about a group of women who've recently joined a running club. You certainly wouldn't want that whole group in the data set because their club supports all of their physical activity, things like that. But let's trust. I'll just say independent data. We need to trust. We need to trust the researchers here. Details would be in that journal article. Details about sampling would be in the journal article. And that is nice when you look at a journal article, as many of you are doing for your journal article part of your project, the methods section often describes in enough detail for a statistically literate person how they built their sample and justifies using the techniques they're using to analyze it. Usually there's randomness involved, and that gets you to independent data. The second assumption is, are all these data drawn from nearly normal population? So, as you think of each group of like coffee levels, is it going to be safe to assume for each group that the variation in metabolic equivalent tasks is nearly normal? Now, they don't give us any graphs of the samples of 12,000 some women drinking up to a cup per week, between 6,000 and 7,000 women drinking from 2 to 6 cups per week, etc. I can't see any graphs that show the distributions of the sample data. With such huge samples, those graphs would immediately tell me if it was safe to assume they were drawn from normal populations. So let me note that first. Nearly normal populations without graphs. Histograms would be perfect. Histograms or box plots would both be good. It's not easy to, it's impossible to see the shapes of these distributions. But there is a clue here. We do have mean and standard deviation for each group. So let's critically think about that, just those of us here for a second. I'm gonna scroll back up. And let me make some more space here. Oh, whoops, not there. Let me just make some more space. There's a lot of stuff down there below that. We'll get to that later. Okay. Pick your favorite column there. I'm gonna go to 2 to 3 cups per day. That's if you translated my tea drinking into coffee drinking, as far as how much caffeine I imbibe, I'm probably in that as a 4 to 6 cups of tea drinker. That translates over to about, because tea has about half the caffeine as coffee, I'm probably in the 2 to 3 cups per day group. Now, let me just show you how I think about possible shapes for this group's distribution. Just with my, statistical know-how, the dream is that it would be a nearly normal distribution. So that would have to be, if the population looked like this, a bell, whoop, right? That's what we want. The mean would need to be, if you're using our sample of over 12,000 women as a good sample, trusting that it's, representative, the mean would be 18.9 right here. Come on, numluck, 18 and 9/10. Oh, I just picked purple because that was the last color I used, but let's have a nice purple illustration here. Okay, and then the standard deviation would be, where's my little standard deviation? You gotta go up this way and back down that way. 22 and no tenths. So this would be 22 and no tenths, that measurement of standard deviation right there. Do you see what I see? Could that possibly be how the shape of the distribution of those women's MET scores look? One reminder for those of you who haven't read this yet, or I've now read it a couple of times, so I've seen this more than once. The MET numbers, MET per week is always positive. It's greater than 0. So see how that standard deviation of 22.0, that would take you down. If you go down 1 standard deviation, if this was a normal curve, that's going to be a negative number. And that's bad, right? To me, this says with the big standard deviation that's bigger than the mean, the metabolic equivalent task scores have to vary. They've got to be skewed off to the right. They can't go lower than 0. So they've got to be skewed to the right. See that? MET can't go below 0. So a normal model can't possibly work. Can't possibly match this mean and standard deviation. Do you buy my little explanation? Is that the drawing close enough to my explanation? Hey, 1 thumb up out of 5. That's pretty good. But if it even made a little bit of sense, like that's how, if I don't have graphs, I look at whatever statistics I've been given, I kind of follow my nose through how it would have to look if the condition was met. I'm critical as I think that I'm critical as I follow my nose. And if I notice something like this, then I'd say the thing's not met. These populations must be skewed. Right. Think about some people exercise a ton. Some people exercise way more than most of us, right? People getting regular exercise are often exercising for, 20 minutes a day is a kind of a doctor recommended amount, though there are professional athletes on planet Earth who tune their bodies and minds and spirits every day for hours upon hours compared to the rest. So let me just grab my little drawing there just for my notes. Be interesting. It can be, in the notes. Everyone reads this later. Let's think that through. Looky there. Now, the fact is, if the data sets are not nearly normal, there's like an amount of skewness that's not too much, but we don't know. So here, let's assume, or sorry, we'd have to assume here, we have to assume researchers are confident that it's not too much skewness to use ANOVA, analysis of variance. That's that one. And the final criteria is, how did they phrase it in our slideshow? Is it constant variation or similar variation between the groups? One of those two, I'm going to say constant variation. That's similar standard deviations is the statistic we have. Well, that's all we can look at, standard deviations here. And hey, now there I'm comfortable. 21 and a tenth, 25 and 5/10, 22 and 5/10, 22 and 22. They're only varying a little bit on this scale that goes from 0 up into, well above, probably well above, at least well above 40. So definitely that looks met. Yeah, these group, all 5 groups have similar standard deviation. Yay, what, yay, yay, no doubt here. Cool. Okay, so that's A and B. And those 2 problems are just reminders, part A, of how the hypotheses always look in ANOVA. we're always assuming the mean is the same for all of the groups. Here, 5 coffee consumption levels. 3 conditions to check: independent data. Data were drawn from nearly normal populations for all 3 of the groups, and similar or constant variation across the groups. Cool. And we depended extra on the statistical numbers here because we didn't have any graphs to look at for the second 2 conditions. Okay, now here's what I did last night. Below is part of the output associated with the test. Fill in the empty cells. Oof. And looky there, there's an ANOVA table. The rows are called coffee. Those are our groups. There's the residuals row, also known as the error row, because E, short for error or residual. And there's the total row. And they've only filled in 3 numbers. The sum of squares for the errors, or in the residuals row, it's over 25 million, a huge number. And the sum of squares for the total row, also over 25 million, but a higher number, slightly. It's like 10,000 something more in the total row than in the residuals row. No information in the mean squares column. F value is not there, but they have given us the p-value, 0.0003 after that decimal. Okay. And yeah, when this is all brand new, figuring out how to fill in these cells can be deeply annoying. Though me and Emiliano Vega of Cascade Campus did give you a tool. So let's put C here. And let's get it up onto the page with our other work. Okay, so someone asked, yeah, how do you fill out this table without the raw data? Great question. Emiliano and I made you this little chart that it's not in section 7.4 from the textbook, but it is in our ANOVA calculations section. All of these formulas are in the textbook, but not all together, but they're kind of nice to have in one place. You can see the degrees of freedom. Every number in that column is calculated based on K, the number of groups we're looking at, and N, the total number of observations. We do have that information up here in our table. So group total number of observations is between 50 and 51,000. And there's 1, 2, 3, 4, 5 coffee groups. So that level's taken care of. The sum of squares column. Oh, plus one more important fact. I didn't put it in my notes. The sum of squares for the group row, the first row, plus the sum of squares error, SSE, or the sum of squares for the residuals row, equals the sum of squares in the total row. These complicated formulas here are only useful if you have access to the raw data and you have the confidence and time to sort through these complicated formulas. But if you have 2 of the 3 numbers in the sum of squares column, as we do here, no problems. We can simply use either addition, or in this case, we'll use subtraction to get the 3rd number. Relaxing. Then the other formulas for mean square and F value, they're here, but I'll just talk to them as we go through and work through the problem. Let me show you how I did. So like I made a table using the table making function of, docs. I made up all the columns: degrees of freedom, sum of squares, mean square, F value, probability greater than F, which is the p-value. And I just filled in the 3 numbers they gave us, right? So I always start with just the same table. If I'm somebody who works by hand, I'd make that on a piece of paper in my notebook. If I'm somebody who's typing, I'm going to type it up on the computer. Now, as a nerd, my next step is to just put in all the formulas I'm going to need in the blanks. So there's the degrees of freedom formulas. K, number of coffee consumption levels, -1. The residuals, degrees of freedom, that's total number of observations minus K. And you can see I've got the numbers typed down below. I'm going to use those real soon. And then in the total row, total observations number N -1. I've got all those numbers right there. Sum of squares column, all I need to know is I can figure out, oops, typo. If I subtract the sum of squares from the residuals row, SSE, from the sum of squares in the total row, SST, I'm going to get the sum of squares for the group row, the coffee row. Relaxing. The mean squares, those formulas, they're typed up kind of weird in Emiliano in my little doc. It says 1 over degrees of freedom for the group times sum of squares for the group. But I wish I'd typed them differently. It's really sum of squares for the group divided by degrees of freedom for the group. So it's just taking the sum of squares and dividing by degrees of freedom. And you do that in both the rows to get the mean squares in both the rows. F value is a straightforward calculation. Mean squares for the group, the number immediately to its left, divided by mean squares from the residuals row, MSE. So the mean squares column looks kind of like a fraction. You just figure out the value, and that's your F score. Kind of complicated, I know, but that's kind of how I kept my notes, just to kind of show everyone these relationships one more time. Now, you can see I'm just plugging in all the numbers as I go. I'm doing some calculations. So this is the biggest graph I've got. See that? There's my 5 groups. Subtract 1, and degrees of freedom for the first row is 4. Degrees of freedom for the residuals, well, we've got a huge number, 50,739 women in the study. Subtract the 5 groups. Yeah, 50,734 is the number in the residuals row. And down here for the total, we've got the total number of women in the study -1, leaving us with 50,738 total degrees of freedom. Whew. And it's no coincidence, the 4 from the first row plus 50,734 in the second row does equal, for the total row, 50,738. A little double check that I didn't make a typo or a little mistake in those arithmetic things I did. Second column, they gave us the very big numbers in the 25 millions for the total sum of squares. I typed that number up here with no commas just because I knew I was going to copy and paste it into Google to do some calculation. There's the sum of squares for the total row, subtract away the sum of squares for the residuals row, and that leaves me with 10,508, the sum of squares for the groups, the coffee sum of squares. Okay, that's the most complicated number to get as far as typing, because you're talking about millions and millions there. For the mean square column, relaxing, we just take sum of squares divided by degrees of freedom for each row. In the group row for coffee, there you go. Sum of squares was 10,508 divided by degrees of freedom 4. It gave us a nice whole number, 2,627. Okay. And then in the residuals row, we've got the much, much bigger sum of squares. It's that 25,564,819. Divide that by the pretty big degrees of freedom, 50,734. That does give you a number with a decimal value after it. I rounded it off to 503 9/10. And then for the F value, the relaxing thing is you just take these two numbers here and do division. So it's 2,627. That's our sum of squares for the coffee row, the groups. Divide by 503.9. Sorry, the mean square was all these squares. 2,627 mean square for the groups. Divide mean square for the residuals or errors, 503.9. and you get a nice relaxing number, 5.213. I think the solution from the textbook said 5.2. They rounded that off to the nearest tenth. I didn't bother to round mine off that much, but they're both great. They're 5.2. The work looks terrific. I got all the numbers, complicated. And then if you wanted to double check the p-value, we could open up GeoGebra, use the degrees of freedom numbers and double check that pans out, though I'm just going to trust our friends who made the textbook at this point. Oof. Now, was that enough detail to get through that big complicated question? Or was it too fast? Anything anybody wants to see me slow down? Because yeah, see there, that last step was a lot at once. So any questions about any of that work in there? Or does that seem good? Tons to work through to get ANOVA to work smoothly in the olden days. Okay, great. Yeah, and there you go. That's the great reminder. We did put that table of all of the straightforward calculations. And don't forget the one more important fact that it's just addition to get to the total row from the two rows above. It's just addition. So that's the crucial fact that helps along with our little table. Table again is in the ANOVA calculations PDF. That's where that lives. Yeah. So yeah, great question. And just a reminder that especially in olden times, before people had access to powerful computing technology, it was like teams of human calculators who would work together for anything bigger than a tiny data set to get these calculations done accurately. And the way they sorted the table out was to set it up so that these total rows would let them double check the complicated calculations for sums of squares that they would work through. Oh yeah. And yeah, I would echo, so glad we have computers in the case of doing math and statistics and analysis of any large group of numbers. Yeah, computers are really good at being told what to do with numbers and then doing it quickly and accurately. So it's a really cool relationship between humanity, math, statistics, and machines. Good old, yeah, good old computers. Plus computers also have YouTube, and you can like, in the morning when you're getting ready to go, you can watch like a philosopher talk about, some philosophy stuff related to current political events that relaxes you and kind of helps you process what's happening on planet Earth. Good job, computers. And great question. All right. Oh yeah, and great observation from Ryan in the chat as well. When you get into the ANOVA calculations work to do that homework for the ANOVA calculations supplement PDF, it's relaxing. You get the data set in the computer, follow a couple of steps, and you get the entire table. All this complicated math gets done just like that, quickly and accurately. You can check your conditions with graphs that pop up right there for you. It is so nice. And yeah, it's statisticians in particular are cool with computers. I mean, the most popular and widely used statistics software is open source free software developed by statisticians over the decades of computer sciences development. It's called R, named after correlation. And it's an amazing suite of software that kind of, whenever you do a stats calculation online, R, the open source software, is kind of getting accessed in the background and helping out things like GeoGebra and Desmos. And heck, even the expensive fancy stats softwares usually use R, the open source version, in their engine. So yeah, volunteers and open source software are crucially important for statistical analysis, and they're used every day by thousands upon thousands of thoughtful analysts. Yay! Good job, everybody. So yeah, GeoGebra, Desmos, R, and plenty of other good online stuff is freely available because people have made it that way, in a cool way. those are kind of the cool statisticians who, unlike Galton and what's the horrible guy from the Gossett, Fisher, those monsters, those guys were terrible. But I mean, as human beings, but the open source community, I'm not sure if they're all cool every which way, but they're really cool in one particular way, building something for everyone to use. That's rad. All right. Pardon me. Let's peek in at the next section. Let's go talk about inference for the slope of a regression line. Let's open that conversation up now, and then we'll talk about it, for the rest of class. Here we go. I'm heading back to slides. Are you getting excited? Look at that. We're almost out of slideshows. Inference for linear regression. Here we go. Ooh, and look at that. We've got a little, I didn't have a slideshow for ANOVA calculations, but you'll like it on Thursday. One of my classes during remote times we turned the notes I was always doing kind of by hand or typing sometimes into a nice little slideshow together. So we'll give some credit to those students next class. I mean, more credit. All right, inference for linear regression's slope. Why don't you like the regressions? I think it's fine. Put that in presenter view and get to the discussion. Remember, inference refers to two kinds of analysis. The stuff we've been working on all quarter, estimating a characteristic you care about in a large group, a population parameter, using a confidence interval. So that's sample statistic with a margin of error. That's one of our inference techniques, confidence intervals. And the other is seeing how likely our sample statistic looks under an assumption about the larger population. That's hypothesis testing. So we can do either one, a confidence interval or a hypothesis test to investigate linear regression's slope. I think the slides focus more. Well, let's see. Let's see what they say. Oh man, speaking of horrible statisticians, Cyril Burt. This guy's among the worst. In 1966, horrible, unethical guy, Cyril Burt, published a paper called The Genetic Determination of Differences in Intelligence, a study of monozygotic twins reared apart. Now, spoiler, when I said unethical, I meant academically. This guy faked his data sets. It's been established over and over that his data sets are kind of impossible. He's a fraud. But he was also he was a fraud who was a good writer and a fraud who told people what they want to hear. Like many statisticians before him, he was also a eugenicist who believed in like breeding people to be better. So he was trying to investigate can we breed smarter people? These are gross ideas that only monsters believe in, though Cyril Burt is one of those monsters and his research supported these horrible ideas. So as we talk through this, I'll just keep reminding you that these twins are fake, the parents are fake, and the data's fake. But the statistical example here is kind of interesting, and it'll let us kind of critique why and how someone would fake scientific work to be a bad person, to support bad ideas. This is probably more important nowadays than it's been in recent decades. Since January, 20th, when we got our new federal government, there have been a series of executive actions, I think they're called, where the president of the US has signed a very long document that sort of puts the kibosh on the current thrust of our scientific understanding of the Earth, whether that's responding to global climate change, or whether that's, giving, having healthcare available to trans kids. Like these are scientific and health questions that shouldn't be political. But when someone with power wants to make changes to maintain or increase their power, sometimes they target either the planet, in the case of ignoring global climate change for business interests, or in the case of using anti-trans bigotry to build a political movement. These are some of the ugliest things that can be done, and Cyril Burt is an example of someone who would use fake science to justify these kinds of ideas. Heck, I got a letter from the Department of Education started off, "Dear colleagues." They sent this out soon after the new Department of Education chair, or what, cabinet lady, the leader of the Department of Education. She's the wife of Vince McMahon, the horrible monster who runs professional wrestling. Her letter basically said, you're not allowed to even consider that there might be any racism happening in any aspect of education, because that would be racist. Just think about how bad of an idea that is for a second. How can you say it's racist to consider how racism impacts people? That's a weird idea. That's considering how racism impacts us is anti-racism. So her letter is about ending anti-racism in education with some ugly fake scientific justifications. So Cyril Burt's not alone. There's still bad guys doing this kind of work today. So let's just kind of dislike Cyril as much as we need to as we go. I'm going to use him as a, he's punchable. I'll just put it that way. Now, all that being said, his fake data set consists of fake IQ scores for an assumed random sample of 27 fake identical twins. So each of those data points is a pair of IQ scores faked by Burt for his data set. One of the fake twins raised by their biological parents. So you can see a wide range of IQ scores as low as 68 and up to about 130 for fake twins raised by their fake biological parents. And you can also see a similar range from a little below 70 up to around 130 of fake IQ scores for the fake twins raised by their fake foster parents. I know saying fake is more accurate, but it sure is annoying to say it all the time. We'll just remind ourselves at the end that it's all fake. But see, we can see the graph here. That is strong, positive, linear correlation. Correlation score is over 88%. So it reflects not much variation away from and around that line of best fit. All right. And nature or nurture, that's the question that eugenicists love to ask. They always want to say it's nature. They always want to talk about nature. Especially when it comes to class differences, gender differences, racial differences, etc. The differences that truly are social, eugenicists want us to believe they're natural. They're just not. Okay, now, which of the following is false in a statistical sense? Well, first, be careful. Look at this complicated amount of information they gave us. We met a couple discussions back the ANOVA table, a table with multiple rows that gives us the output for ANOVA analysis. This is a regression table, a complicated table that gives us all of the output when a stats software does regression analysis. Let me just show you what's what here. Some stuff is labeled pretty clearly, like residual standard error. That's a nice label. That's the standard deviation of the residuals, and it tells you their degrees of freedom. It's 2 less than the sample size. It gives two kinds of R squared values, multiple R squared and adjusted R squared. The one we think about is, I think, multiple R squared. It's just the square of the correlation score. There's a related F statistic if you care about F values. And there's a p-value down here, 1.204 E negative 09. Same p-value with this F statistic that we see in the bio-EQ p-value row. That's a lot. And that's just the stuff that's labeled carefully. Up here at the top in the coefficients zone, there's a row for the intercept. So remember, we have two important numbers in linear regression, the intercept and the slope. First thing you want to know is that second row, it's labeled bio-EQ, but that's the name of the X variable here. So, it's always the name of the X variable is the slope row of the table. Now, the estimate column of the table, these numbers here, the intercept for linear regression is right there. So for this sample, that is the intercept. And for this sample, that number there is the slope. Symbolically, they're called B0 and B1, right? Oh, maybe I should change my style here. B0 is that number right there. And B1, come here, give me my little arrow, shrinky dink. And B1 is that number right there. Those are crucial numbers. If you're looking at this big table, you can see now that our relationship is Y with a hat. So that's predicted fake IQ for a fake twin raised by a fake foster family. So predicting, you'd start with 9.20760, or you could round that off if you prefer, and you'd add that slope value 0.90144x. So there's the regression equation, right? It just comes right out of the estimate column. That's important. Without knowing that, it's really difficult to talk about the questions below. We'll talk more about the standard error column, the t-value column, and the probability or p-value columns. All of those will get talked about more as we go forward. Here, they're focusing us in on which of these statements is statistically incorrect by what we know about linear models. So, and for false, I'm going to use a red strike for false. So the actual choice we're looking for here is going to be a red strike. Let's take them one at a time, A, B, C, and D, and figure out if they're true or false as we go. All right, part A. Additional 10 points in the biological twins' IQ is associated with additional 9 points in the foster twins' IQ on average. Let me round off my numbers up here so they're easier to read. Let's call the slope 9/10, and let's call the intercept 9 2/10. They're easier to read. Is that true or false? Remember, it's the slope that tells us about the prediction when you change one value, how that should affect the response. Does that seem right? If you bump up by 10 biological twins IQ, that's the X value, are you going to get back 9 points higher foster twin IQ with this equation? Yeah, good eye. Okay, yes, great. Yeah, this is true. That's just using this number, this equation, and a little thinking about what the slope means to describe the relationship. Here's an aside. In the fake study, the biological twins were raised generally in more wealthy homes. They were raised by wealthier pairs of parents who, for some reason or other, only wanted to have one kid and gave the other up for adoption. See how fake it sounds? That's weird. But the twins raised in foster settings, they tended to grow up as foster kids actually do in real life, with less access to wealth. So this is saying that when you bump up a child raised in privileges IQ by 10, you would expect the same child raised with less privilege to be a little bit less intelligent. See how that works? See how eugenics works? It's gross. Okay. Part B, roughly 78% of the foster twins' IQ can be accurately predicted by the model. The only 78% we see in these numbers is this R² value right here. We only talked briefly about R² before. Remember, what R² tells us is 78%, sorry, R² tells us the percentage of vertical variation in the graph that happens along the line of best fit. So what that says is, if I'm going to put it in language here without looking at B, I'm going to ignore B. R² means about 78% of the variation in foster twins' IQs in these fake data. 78% of that variation happens along the line. See, as I kept saying 78% of the variation. Let's look what they say here. 78% of their IQs. That's not the percentage we're looking at. We're talking about a percentage of variation, not IQs. I think B's false. Spoiler. Yeah, that's false. B is false. Okay. And then the last two, they're not as complicated as the first two. The linear model is they're just using more complicated note-taking than me. Foster IQ, subscript predicted. My symbol above was Y with a hat, equals 9 2/10 plus 9/10 times biological IQ, which I just used X. So that's just a different way to write the equation. And D, foster twins with IQs higher than average IQ tend to have biological twins with higher than average IQ as well. Keeping in mind that all of these data are fake, that just says the slope is positive. This is a positive relationship. When one number's higher, you expect the other to be higher. No shock from the way the graph looks. But pretty complicated to get through the table. And yeah, there's some complicated stuff here. But if I'm going to highlight one thing here, it's when you want to know this regression equation, you get those two numbers you need for slope and intercept right here out of this estimate column. That's crucially important. So intercept is labeled nicely so you can see the intercept row, and just knowing in your heart that it's the slope is the second row there. And you've got that part of this table in your working knowledge base for homework for this week. Okay, let's take a quick break, or a normal break, because it's about halfway through class, and then we'll come back and talk more about regression and inference. We're going to get to these other columns: standard error, t-value, and probability. Oh yeah, and Lauren R. already asked the question in the chat. Does the p-value for the intercept matter for anything? Not a lot, not very much, and we'll talk about why that is more in a few minutes. So let me just put us back to the home screen for a nice, easy way to navigate the break on the YouTube. And we'll be back in 10 minutes. That's 13 minutes past the hour. So see you soon. Very good. Look at that. Look what we did. Look at that. Very good. How is it possible to believe it? I was talking to somebody during the break, yet I'm still back on time. The person walked me back to the classroom while we still talked. Look at that. Look at our instincts. Jeff Wax. Guy knows how long 10 minutes is. All right, cool. We are back. It is 13 minutes past the hour. Let's go back and talk more about inference for linear regression. Before the break, we met the big, messy linear regression table, and we focused in on the important place. This zone is where you get the slope, 9/10 right there, and the intercept, 9 2/10 right there. Nicely labeled so you remember which is which. When you want to do linear regression work, especially in this chapter of our text and in the work we'll talk about on Thursday. You'll see lots of these tables. Okay, assuming that these 27 fake pairs of twins comprise a representative sample of all twins separated at birth, quite a big assumption considering that it's all fake. Researchers would like to test if these data provide convincing evidence that the IQ of a biological twin is a significant predictor of IQ of the foster twin. What are the appropriate hypotheses? Let me just remind you what all those B's and betas mean to sort this out. Remember, B naught is slope estimate. So from, or no, that's wrong. Interval is not slope, not. That's is the intercept for sample data. Beta not. I can't type a beta on my computer, but that's the Greek letter beta. Beta is the intercept for the population. B1 is the slope for sample data. And beta, Greek letter beta, 1, is slope for entire population. Whew. Let's make sure all those symbols are there for us so we don't have to try to look those up in our notes. And I'm not going to force your eyeballs to search through here. Let's work on this together. Let me read the question again. Assuming these fake data are not fake and are useful, we'd like to test if these data provide convincing evidence that one twin's fake IQ can predict the other twin's IQ. Which number do we use for the prediction? Which has more impact on prediction? The intercept or the slope? Which number has more impact on prediction? The intercept or the slope? Remember that previous slide? There was so much mess on it, but see here, A, that's prediction, right? Additional 10 points in biological twins fake IQ is associated with additional 9 points in fake foster twins fake IQ on average. That's prediction, and it's based on that 9/10. 9/10 of 10 is 9. That's prediction. So we're talking about the slope. Okay. Now let's go back and sort things out. We're talking about the slope. So goodbye to B1. Sorry, goodbye to B naught. That's intercept. Bye-bye A. Goodbye to intercept beta naught. That's B. We're making an assumption about the slope for hypothesis testing. When we set a null hypothesis, is it going to be about a sample or about a population from which we've drawn our sample? Is the null hypothesis about a sample or is it about a population? This is just in general. Every null hypothesis all quarter. Hypothesis testing. The goal is to get a p-value that shows us how likely our current data set looks under a null hypothesis assumption about the blank, sample or population. There's so many Greek letters and other letters floating around. And it's early on a Thursday. Oh, is it Tuesday? It's Tuesday. Pick that up. Oh, someone's got their idea in the chat via direct message. But let me type out my little sentence again, see if we can get one more person to share their idea. And hint, you're not wrong in the direct messages. You are not wrong. You are correct. Hypothesis testing. How do I say it? I'll do it this way. Hypothesis test gives us a p-value, a probability p-value, probability of how likely our current data set would be under a null hypothesis assumption about the blank. Fill in the blank, sample or population. We've got one correct person in the direct messages. And hey, we've also got one correct person in the chat. Yeah, it's the population. It's always the population. We always make our null hypothesis assumption about the population. That is crucial. So, if I could turn that bold, maybe I should have typed it in all caps or something. But knowing that, we can just, in this setting, we can kick out everything that says sample. So we already kicked out B0, B0, but we can kick out B1. That's the sample symbol. So goodbye option C. I think the valuable thing on this slide for me is that this reminder, every hypothesis test, the null hypothesis is always about the larger population. Just having that concept deep in our statistical knowledge base, as holding on to it with our hearts is crucial. The symbols and all the numbers and situations are easy to distract us from that important concept. All right, like here, there's a bunch of symbols distracting us from the important concept. But they're saying here, the idea would be for a null hypothesis, H0, assume there's no prediction relationship. And if there's no predictive relationship, that means there's no correlation. Correlation gives you a correlation score of 0, and that gives you a slope of 0. So for the population slope, beta 1, it should be assumed to be 0, meaning no linear correlation, no predictive relationship. Alternatively, assume the slope beta 1 is not equal to 0. It could be positive for a positive relationship or negative for a negative relationship. Okay, testing for the slope continued. There's the same regression table we saw before, just typed up in a different font, and they've left off all the information about R squared and other statistics below. Oh, that's a good T. Oh, it's good, it's good. We always use a t-test for inference for regression. T-tests make sense because we're talking about two numerical variables, and the regression equation gets drawn using their means and their standard deviations. So when we're in the world of means and standard deviations, we're in the student t-distribution world. T-test is what works for inference for regression. And now the test statistic, t, has got to be your point estimate, subtract away your null value, and divide by standard error. Now you're going to like this. Watch what happens here. The point estimate for the slope is just B1, observed slope. That number is B1. That is the point estimate right there. Slightly more than 9/10. Okay, and so wait, sorry, I didn't get all of my point estimate. B1, there it is. The null value we saw on the previous slide assume the slope is 0. So the null value, let me just grab a, I don't know, red, and just draw a little 0 on top of it, because that's not going to really impact the calculation much. Standard error, subscript B1, standard error associated with the slope. Not hard to find that number. I'm just going to highlight it everywhere it pops up. Standard error associated with the slope. That's going to be this standard error in this setting. Well, it's just right there in the same slope row, 0963 after a decimal. Are you starting to see how relaxing the t value calculation is going to be? We're just going to take the estimate, 9014 after a decimal, subtract nothing from it, and divide through by the standard error, which is right there in the table as well, 0963 after a decimal. Oh, degrees of freedom for the test, 2 less than the sample size. That's because there's 2 estimates here, the estimated slope and the estimated intercept. So that's just a little analytical note. Degrees of freedom, n equals 2. And then, oh, what I said out loud, we lose 1 degree of freedom for each parameter we estimate. So here there's both intercept and slope. Beta naught and beta 1 from the population being estimated there in the table. Oh, did you really? Oh, they have their own color scheme. Oh, I wish I knew their color scheme before I did all that coloring on the previous slide. Now I feel a little embarrassed, but watch them go through the numbers here. T, when they plug in the numbers, so there's the slope estimate, subtract away the 0 from the null hypothesis, no impact there, divide through by standard error. Now the number is bright green, 0963 after a decimal, and you get back the test statistic, the t-value, 9 and 3600ths, rounded off to the nearest hundredth. And that number, when we plug it in to the degrees of freedom, 25 student t-distribution, and do a two-tailed hypothesis test. So let me go look at that, geogebra.org/classic #probability student t-distribution, 25 degrees of freedom, two-tailed test, 9.36 is my t number. So I'm going to go below negative 9.36 and above positive 9.36. And for the eagle-eyed among you, you could have already seen the area estimate was going to be 0 just by looking at that student t distribution and noticing it's hitting that, or it's getting very, very close to that horizontal axis already around 4.5 on its scale above and below its center. So when you go out to 9 plus in both directions, there's really no area under the curve that far out, at least not enough for us to care. Rounds off to 0 at 4 decimal places. And that's our, well, p-value in the textbook, they'll just say it's going to be using the t tables in the back of a book, less than 1%. Well, we know it's less than 1/100%, and it's less than 1/1000%. It's a tiny number. 0.0000 is where it rounds off to. So it is low, 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 low. Oh, and there you go. That's how you get a p-value for linear regression slope. You just gaze at this table. So like when you want to do linear regression slope hypothesis testing, the p-value just pops up right there. The test statistic right there. And the slope value itself is right there if you want to make a prediction. So yeah, here we're going to reject the null hypothesis. We've got evidence. There's a predictive relationship. There's correlation between Cyril Bert's fake twins' IQs raised in wealth or raised in relative poverty. Pretty gross. Pretty dang gross. Yeah, I'd call it gross. Now, how surprising was that result? Let's go back and look at the graph. So just put a little note up here. Assuming no correlation, we get p-value close to 0. So we reject that assumption. Evidence of correlation. That's what happened in language I can put at the top of the slide, okay? Now let's go back to Cyril Bert's fake data graph, the scatter plot, all the way at the beginning. Whoop, there it is. Was that about the most boring hypothesis test we ever did? We can see positive, strong linear correlation right here in the graph. That p-value very close to 0. It's like, yes, it's statistically significant evidence of correlation, but for me, the graph, my eyeballs already showed me that there's positive correlation. I didn't really feel like going and doing a hypothesis test. We'll talk more about the slope in the next section, because what I'm more curious about is putting a little wiggle on that slope, a little margin of error. That's more interesting to me as an analyst, although I'd rather not do it with a completely fake data set. So let's move on from this monstrous eugenicist's bad data. You will, though, and speaking of bad guys, you can kind of tell if someone's a bad guy in terms of being a monster who uses science to hurt people if they defend the work of Cyril Bert publicly. It's a good tell that someone is just not looking for progress, fighting racism, fighting sexism, fighting classism, or fighting anything else that those ugly eugenicist monsters propagated in our culture. Okay, now, and then here, our second example is also about race and ethnicity and correlation. This one's a little different though, because it's modern. It's a data set probably from around 2012. And here we just want to tread lightly. No one's obviously committing fraud, but we want to think about what these conclusions might mean as we go in terms of racism or anti-racism. We've always got a choice how we look at data sets. So let's go in here treading lightly and being thoughtful in our analysis. We're studying the percentage of college graduates in the zip code areas of Los Angeles. So the two maps show the zip code areas of Los Angeles. The map on the left shows in each zip code the proportion of people graduating from or who have graduated from college. I hope they're not including people who are too young to have graduated. That would be weird to have them in the data set, but I'm not exactly sure how they get the number. But you can see the darker counties here. A county like this one, let me just point with my arrow. Darker counties are closer to 100% college graduation rate. That'd be like, that's about as dark as they get to my eyeballs right there. That county, or sorry, that I call them counties, but they're zip codes. That zip code and counties with very low college graduation rates in terms of percentages are light colored. And there's tons of neighborhoods like that. I could pick, say, I don't know, that one, for example. It's just the first one that comes to mind as I track away from that very, very high college graduation rate over to this. That's the nearest, or maybe even that one. That one's pretty nearby. Those two have low graduation rates, right? And they're nearby that zip code with a high graduation rate. Over on the right-hand graph, you can see instead of graphing college graduation rates, they're graphing the proportion of people who are Hispanics, people of Hispanic origin. That's an ethnicity, not a race, at least in the way that I've been taught about race and ethnicity. Like, I'm white racially, and I'm also not Hispanic. There are plenty of white people who are also Hispanic. Similar for Black people, there are non-Hispanic and Hispanic Black people. See what I'm doing here? The racial categories tend to be based on white supremacy and colorism, whereas ethnic status, like being Hispanic, is about where you're from, the language group you speak, like Hispanic people come from Spanish-speaking regions, stuff like that. So people from Spain are Hispanic. Lots of them are white. People from, the Dominican Republic are Hispanic. A lot of them speak Spanish and lots of them are Black, right? All right. In any case, here's the graph. We can look in and you can see here, high proportions are high proportions of Hispanic people in those zip codes. There's a very, very extremely high proportion of Hispanic people living right there. That's great. Must be a fun neighborhood. I mean, all the neighborhoods of LA are fun. It's LA. Come on, it's nice. But and you can also see neighborhoods that have very, very low proportions of Hispanic residents. I don't know, like that one jumps out of my eyes. It's on the edge of the map and it's very, very low. See that? All right, that's how the graphs work. Can you track with your eyeballs the trend here? Can you see the trend? Or do you want the scatter plot? You want a scatter plot to see the trend, or do you want to track it with your eyeballs right here? Oh, we have 15 minutes. Well, I don't know. If you just pick a random zip code like that one, I'm pointing at this dark one, so that's lots of college graduates in this one right here. Over here, I can see very low proportion of Hispanic people. Let's look at some of the ones I looked at before. That was the highest proportion of Hispanic people that jumped out of my eyeballs. It has a relatively low college graduation rate. I think I picked that as my highest college graduation rate. There's nearly no Hispanic people living in that neighborhood, that zip code. And the nearest very low proportion of college graduates has also a very high level of Hispanic people. To me, doesn't that look like a negative relationship where you see a light zip code here, it's dark there, and where you see a light one over here, like it's not always, well, it's not always true. Some of them, like that's about the same color here and there, but that's dark and that's light. See what I'm doing? See what I'm seeing? This one's light and that one's a little light and a little dark, but some of them, like that one's light and that one's pretty light. But there's a trend. You can see light, dark, but sometimes light, light. There's general trend though. Let's look at the scatter plot. Go clear trend. Okay, If you graph it, percentage of Hispanic people on the x-axis, make that the explanatory variable. And you make the percentage of people in the same zip codes who are college graduates the response variable. You can see the negative relationship. So some zip codes have, the zip codes that have very high graduation rates, or the highest graduation rates as a cluster, are up here, and they also have the lowest proportion of Hispanic people living in those neighborhoods, with the exception of this county, or sorry, that zip code. It's about half Hispanic people and extremely high college graduation rate. But then as you get over to the very high levels of Hispanic people in the zip codes, they have generally the lowest graduation rates, a strong negative relationship in terms of correlation. If I draw my line of best fit, it's going to look something like that. Something. That might not be steep enough even. Or like that. We'll probably see the line on a future slide. Let's go learn more. That's the graph. Oh, is there any causation here? Any causation at all? No, important, right? This is correlation. We're looking at just two characteristics of these zip codes. There's a ton of historical and I mean history going right up until today and through into the future, historical reasons that Hispanic people live in different zip codes. And there's also economic reasons, there's cultural reasons, there's tons of reasons. And there's tons of historical, cultural, and personal reasons that people graduate from college or not. So there's so much more going on here that's not in the graph. It wouldn't even be sensible to think that either of these two characteristics has any direct impact on the other at all. Though we will talk about the relationship in terms of what we can learn from it as far as a correlation. Okay, but here's again, we're back in the, oh, I want to get my light back, hold on. We're back at the linear regression table now. So here's the regression table for this relationship. There's our estimates of the intercept. It's about 729 after a decimal. Oh, farewell, direct messenger. Have a good one. And there's our slope estimate in the second row, negative 7527 after a decimal. We got the standard error column for when we need it, the t-values if we care about them, and both of our p-values, which, we still haven't talked about that p-value for the intercept, but we'll mention that before we leave for sure at some point. But let's focus here. What is the interpretation of the slope for this model? The slope, remember the slope is the estimate in the second row, that one. And translated into the language of this problem, that would be negative 75 hundredths of a percent with slope units attached beyond percentage. So they've got some options here. Oh, and remember the basic slope interpretation. Basic or generally slope predicts change in response variable y for a 1 unit increase in explanatory variable x. So remember, explanatory variable here is the percentage of Hispanic people living in a neighborhood, or sorry, a zip code. Response is the percentage of people graduating from college in a zip code in LA. Whew. I can eliminate D. I read them all. I just using my eyes to look for anyone that's bad. See D, it's the only one that doesn't talk about a 1% increase in Hispanic residents. So yeah, no Hispanic people in a neighborhood. That's not gonna have anything to do with the slope. That's just a, I don't know what they're talking about there. So don't worry about that. All right, let's look around here. Oh, I can help you out too. Because of the units percent Hispanic, that's negative 75 hundredths. That's 75, or that's 0.75%. So this 75% has got to be wrong. It's too big of a number. Let's look at B and C in detail. Oh, we've got to vote for B. Let's read B out loud. That's exactly where I was going, just to read it. A 1% increase in Hispanic residents in a zip code area in LA is associated with, think of correlation, not causation, a 75 hundredths of a percent decrease in the percentage of college grads. Yeah, negative slope, decrease, correct units. I like B. Let's check Lauren R's idea. Yeah, good. B is good. C is worded only slightly differently, but I can show you why it's bad. See how it reads: an additional 1% Hispanic residents decreases the percentage of college graduates. That's like one variable directly causing a change in the other. That's the language of causation. So no, too much causation in C. You got to focus on prediction. Predicting is fine. Talking about correlation is fine, but don't talk about increasing one directly impacts the other. Language-wise, it can be a challenge to get these perfect, but just keep practicing in your work and ask me if you've ever got a question. Okay, do these data provide convincing evidence that there is a statistically significant relationship between the percentage of people who are Hispanic and the percentage of people who are college graduates in zip code areas in LA? Now remember, to do this, our null hypothesis is going to be assume that the slope beta 1 for the whole population of all the people living in all the neighborhoods of LA is 0. That is, there's no statistically significant relationship. Correlation is 0. And then alternatively, assume that slope beta 1 for the whole population is non-zero. What do you like? That's a classic not equal to slash through a long equality symbol, not 0. And remember, the p-value for this particular pair of hypotheses, the p-value lives, it's because we're in the slope row, the p-value for that exact hypothesis test is right there. So what are we going to do? Reject the null or not? Yeah, p is low, the null must go. Let's reject it. Good chat, good work. P-value for percent Hispanic, the second row is low, like 0 to 4 decimal places, indicating that data provide convincing evidence the slope parameter is not 0, that there's correlation between these two characteristics. Now, again, how exciting is that is my question. Let's go back to the graph. Like just grabbing any pen I've got on planet Earth, if I trace through this cloud, up until we run out of room down there in the corner where you can't go above 100% or below 0, I can just see strong linear correlation. So this null hypothesis that the slope of the regression for if you include everyone would be any different than 0 seems crazy. It seems like a crazy hypothesis to make. These hypothesis tests for correlation for slope being non-zero might be the most boring hypothesis tests we've done all quarter. Because if you just can see the relationship on the graph, nearly every time you're going to come back with a p-value of 0. It's just how it works out. Now, there is one more little detail here. Wait, put that there. How reliable is this p-value if these zip code areas are not randomly selected? Oh, if they're not independent. Yeah, go ahead and switch the question mark to an exclamation mark on that chat, Lauren. Oh, not reliable. You'd want to have a random group because, yeah, there's reasons, again, historical, cultural, personal, social. There's a lot of history in LA, reasons that Hispanic and non-Hispanic people live where they live. And if you're looking at all of the zip codes, that's really the population. So maybe you shouldn't be doing hypothesis tests about the population if you've got all of them. And if you're looking at a large group, like every zip code for which you have data, that's not random. So you might want to pick a random subsample about as big as you like, and then do your analysis. So yeah, you got to be careful. Random sampling is key to maintaining independence. So just watch out for that. Now, oh, look at that. We're right there at the end, 10:49. And there's another topic here, but it's a perfect one to start off next class. So let's pause here. Next class, because these hypothesis tests are wildly boring. Like you can see there's relationship there on the graph, so why bother with the p-value? Who cares? Though on the next slide, it's okay, let's put some wiggle on the slope estimate so we can talk about it in terms of, our prediction can have some wiggle on it that's thoughtful and based on our sample size and how confident we'd like to be. That's more interesting, and we'll talk about that to kick off our discussion on Thursday. See you Thursday for confidence interval for the slope. And if you have any questions between now and then, just let me know. I am going to go turn on my Zoom room. This one right here, that little Zoom link will be open for the next hour or so. Should be turned on by 11. And I got to turn it off at noon to drive home. So come stop by if you have a question. And if not, I'll see you Thursday. Farewell. Hey, and you're welcome, and thank you for your work.